Okay, so as we talked about last week, so basically this week you should be working on getting the data for your calibrations for your skeeter sats. And then, once you finish that, you want to start actually writing your reports. And we just want to cover some real basic introduction of errors and uncertainty. So there'll be this lecture today, and this is sort of an attempt to focus on the stuff you should be thinking about while you're taking your measurements. And then on Thursday, there will be another lecture that will talk about some of like fitting and, basically more data analysis type ideas of errors and uncertainty. So this is the first part of, just a quick intro to errors and uncertainty. This is, a very complex topic. There's entire textbooks on statistical analysis and error analysis. And this is something that even, scientists, who have been many, many years working in their field often, have trouble with. And by no means is this definitive, but really good error analysis is really challenging. So one thing we want to be clear about is, what do we mean when we talk about error? When we say, the error on this measurement is XYZ, right? And when we talk about error in scientific measurements, what we're actually doing is we're making a quantitative statement about, what the accuracy of our measurement is, right? So we're basically trying to give usually some kind of interval that we have a reasonable level of confidence that the true value of whatever we're trying to measure is within that interval. So like I said, it's, a quantitative numerical statement. It's, something along the lines of, I think there's a 95% chance that the height of that tree is between 10 and 12 feet. And I think it's most likely 11 feet, right? That's what, if I was to say the height is plus or minus 11 feet plus or minus 1 foot, that's really what that means. Now that percentage may change. So it may be 67%, it may be 95%. That's something that sort of depends on the level of analysis you're doing. But so the thing to remember is that basically any sort of real measurement or any sort of measurement is going to have some uncertainty to it, right? There's going to be some sort of error and by error, we mean inexactness or random statistical spread, right? Now, when we say error, we don't mean like, oh, this is an incorrect measurement, or a lot of times, undergraduate students will like to just throw in the phrase human error, and then, well, what does that mean? And that's usually also that means, well, if the value is wrong and you have a reason to suspect it's wrong because you've made a mistake, you shouldn't use it, right? You shouldn't just make a blanket statement like, oh, there's 5% human error. That's sort of a meaningless, and you can only really do that if you're like comparing something to like an accepted value, right? And you want to understand why you have a difference like that. So in general, when you're dealing with errors on scientific measurements, they broadly fall into two different categories. And this is the first category is the random or statistical error. And then the other is usually called systematic error. And obviously the random error is a random error. That's called that for a reason. It's a random fluctuation around a a true value or a mean value, depending on how you want to think about it. And this is assumed to follow some sort of statistical distribution, right? This is where you'll see a bell curve or a Gaussian distribution, but those aren't the only ones. There's all kinds of different statistical distributions. But because they follow this, mathematical distribution, you can actually make mathematical statements and do calculations on those errors. And because it's random, you usually expect that error. If I make several, measurements, I expect that error to average out to zero. So like, sometimes it's going to be high, sometimes it's going to be a little bit low. So if I repeat the measurement over and over, I can then take the average of those measurements and, sort of reduce the effect that statistical error has. So, there's a lot of different ways that this can happen. Often you're using some sort of electrical device, and if you're making a measurement of sufficient precision, right? If it's sensitive enough, you'll see random electrical noise. It could be that you have a little bit of parallax and, just I'm not looking at a gauge straight on, and you would expect that to probably be random because I'm going to, depending on where the needle is, I'll be looking at it slightly different. But there are also a lot of actual physical processes that'll give you random error. So like radioactive decays, or you're counting individual photons, or you're dealing with something where actual quantum mechanics has an effect. Those are going to have actual real random processes that are going to introduce a random, uncertainty into your measurement. So the other major type of error is systematic error, and it is, not random error. It's the sort of thing where everything in the world is either a duck or not a duck, right? So all of the errors are either random or they're not random. So we lump all of the not random errors together, and we call that systematic. And because it's random, it's not the sort of thing where you would assume, it will average out. And because it's, often a fixed amount, some fixed uncertainty, or there's no particular mathematical model that you can usually apply to this systematic error. And because of that, you sort of have to treat it separately, and you can't do the kind of mathematical analysis that you can do with the random error. So like, for example, you could have something that, a slightly miscalibrated gauge that always reads a little bit higher compared to other gauges. This is also where you would sort of lump in the limit of your resolution of your measurement device. So if I have I'm measuring the length of something measured in a ruler that's marked off in millimeters, I would, assume that that has a minimum resolution of like 1 millimeter, maybe half a millimeter. And that uncertainty is not going to get smaller. I can't average that out because it's the limit of the actual tool you're using to measure. So like I said, with that random error, you can actually do some mathematical analysis on it because it's assumed to follow a mathematical distribution. So this is where you would start to get into the first thing that people see is the standard deviation, right? So if we repeat the measurement several times, we can look at how much that's spread, how wide of a spread there are between these multiple measurements of the same thing. And that's where your standard deviation comes from. But you need to have a repeated measurement to be able to, have any sense of that. If I just do a single measurement, so if, for example, I take a SCEDARSAT measurement at a particular temperature, and I only look at the frequency output, a single set of frequency output, right? I can't really tell anything about the uncertainty because I only have a single measurement, right? There's some random spread, and if I just picked one thing in there, I have no idea how wide that spread it is. Now, there's actually two important standard deviations that you should run into, you'll see. So usually when people say these, just say standard deviation, what they're actually talking about is the the sample standard deviation, which is given by this equation over here, right? So what you're doing is you're basically, each of these xi's is the individual measurements, and the big X here is your average of all those measurements, right? So you're seeing, so this term in the sum is just, I take the difference between the mean and all of my measurements and square it so it doesn't go positive and negative. And then I divide it by the number of measurements over 1, right? But the key thing to know about this is basically the error and uncertainty in a single measurement, right? It tells you how much scatter I expect to see from one measurement to the next. The standard deviation of the mean is exactly what it sounds like. It's the error of the mean. So if I'm taking the average of all these values and I want to report an error for it, I want to actually use this standard deviation of the mean, which is the lower equation here. And it's basically, it's just the sample standard deviation squared over the number of measurements, right? And you can see, well, it's not very obvious, but the sample standard deviation is going to eventually, if I take lots and lots of measurements, it's going to reach some fixed value that's going to be determined by whatever that statistical distribution that is causing my error. Whereas the standard deviation of the mean will actually always go to 0 as I take more and more measurements, because I'm getting a better, as I take larger and larger amounts of measurements, they're averaging out better. So my mean is a more accurate representation. So because you can't have a strict, mathematical treatment of your systematics, you sort of have to just sort of argue and logically think about it and try and make comparisons to determine what it is. So for example, you could compare, you could basically take measurements of of an object of known dimensions, if I'm, just doing measured length, width, and height, right? Where I know what the value should be, and I could compare it to what I get. And then I would say, that difference between those two values is what my what my systematic error would be. Also, this is where you're going to factor in things like what is the accuracy uh, based on the manufacturer specifications. So for your multimeters, for basically for almost any piece of test equipment you're going to use, if you look into the manual, at the back, there's going to be a table where the manufacturer gives you some sort of specification of the accuracy. And it may be different depending on which setting you're on, which scale you're on, but you'll often see things like, 1% of full scale, which means if I'm on, the 0 to 200 volt scale, that means the manufacturer saying this should be accurate within 2 volts, right? So I would say my systematic error is as large as 2 volts in that case. It may also be given as a percentage of whatever the output is. And then also sometimes you'll see it phrased as number of digits, in particular with multimeters. And what that means is, like it's times 2 of whatever the smallest digit on that particular scale is. So the other possible way to look is if you don't have those specifications, at least what the minimum accuracy you can read with the device. So like on a ruler, the smallest marking that I can see on the ruler is sort of the smallest accuracy I can say. If it's a digital meter, right, I can only read out to whatever the smallest digit it is. If I'm using an analog sensor, which I'm going to hook up to an analog to digital converter, which is something we'll do later in the semester. Those digital values will come in fixed steps, right? Because you're reading a continuous analog voltage signal with a digital device. So I can only record the value that I'm reading on the microcontroller in fixed steps. So that's going to have some resolution that depends on the particular hardware that I'm using to do that conversion. So for a quick example of, this is something you could do and also just shows you the example. So this is basically 7 multimeters that are hooked up to the same circuit. So these are all hooked up in series and they're all reading the current. And because the current has to go through each one of these multimeters, and it can't like store the charge anywhere, we know that the current has to be the same for all of these different multimeters. But you can see that basically I've got a spread of about 0.5 milliamps, right? The lowest one is 49.7 milliamps, and the highest is 50.2. So, from this, I could say, the accuracy of this multimeter on this setting is 0.5 milliamps, right? Because I know physically these multimeters are all measuring the same quantity. It has to be the same, but I'm getting different values. So why do they not all read the exact same thing? Well, if we look at the accuracy in the manufacturer, they're going to say for this particular multimeter, it's only 1% of full scale. And if you go back, it's a little hard to read, but that's the 200 milliamp scale. So I would expect an error of 2 milliamps. Or sorry, the scale is 200 milliamps. I believe I misspoke. But so we're actually seeing less spread than you would expect just based on that manufacturer's accuracy. Something also you would know if you repeated this is basically each individual meter would read the same value over and over again, right? So that tells you that that scatter that you're seeing is not random. It's not a random error because this is basically a fixed shift with each individual meter. So that's something that you would consider a systematic. And like we said, it's actually smaller than that specified error. And in fact, in this case, you're not really going to be able to detect that random error because the systematic error is so much larger. The resolution on your multimeters is larger than whatever that random error is. So if I take any one of those individual multimeters and I try and take the standard deviation, is basically going to be 0 because that 0.1 milliamp resolution of that multimeter is larger than the random error. So this is something, you want to think about when you are going in and taking your measurements, right? We want to try and choose tools and choose the experimental setup in a way to minimize these systematic errors. So one thing that can actually also cause systematic errors is, how you've set up your experiment. So for example, in the case of the SkeeterSat, if I have the thermometer resting against, say, the glass beaker, if I'm using a water bath, whereas my temperature probe of my SkeeterSat is sort of dangling free in the water, well, the glass is getting heated directly, so it's probably going to be hotter, which means my temperature is going to be consistently reading a little bit higher than the actual temperature being sensed by the SkeeterSat temperature probe. And that's going to be a relatively constant shift, right? It's not random. Also, another way that this could happen is if you're actively heating or cooling, or particularly if you've got a hot water bath and it's just having losses to ambient, right? Depending on how long it takes me to check my thermometer and then record the sounds, if there's a time gap between those two things, I have a changing temperature with time. Now I'm, basically introduced a little bit of systematics because I've heated up or cooled down in the time between those two measurements that are correlated. Now, obviously, you're not going to be able to create a perfectly insulated water bath, but you want to get a sense of how quickly is that temperature changing, and is that change large enough for you to be concerned about it? Or is it, like, okay, yes, it's cooling down, but it's taking 5 minutes to change, drop a degree, and my two measurements are within 5 seconds of each other. So the actual change that occurs between my sound measurement and my thermometer measurement is negligible, right? But this is the sort of things you want to be thinking about when you're taking your measurements. And also, this is the sort of stuff you should be writing down in your lab notebook, so you can then, when you're writing your report, address these things. So like I said, you want to try and minimize the systematic error because it basically sets a upper limit, or a upper limit on the or lower, it sets a limit on how accurate your measurement can be, right? Because you're not going to be able to take, no matter how many times I repeat the measurement, the systematic errors are going to be the same for a given experimental setup. So, you want to use whatever the most accurate test equipment that you have access to that's reasonable to use on the measurement. You want to, because the error on most digital equipment generally scales with the scale, you want to use the smallest scale or the highest resolution that is appropriate for the value, right? So if I'm trying to measure the voltage of a 1-volt battery, it's better to use the 2-volt setting or as opposed to the 20-volt setting. If there is some sort of time dependent thing that's happening, I possibly want to use something either to slow down that time dependent change, so I could insulate my water bath, or the fact that we're going to use a water bath itself as opposed to like heating up the air, right? Because I could easily stick a heat gun and put the temperature probe and a thermometer in the stream of the heat gun, right? But that air is going to rapidly heat and cool up much more quickly than the water, right? So it's going to be really hard to get an accurate measurement and also get a consistent temperature within the volume occupied by my thermometer and my temperature probe. And also you want to try and be consistent about the way you take your measurement. Or you can try and take mitigating steps so you're not, shifting the scale by reading it a certain way. A really good example of this is if you're using a mechanical gauge, like a pressure gauge, you want real high precision, because that's basically a needle moving in front of a scale. If I shift my head to one side, I can make the needle read a little bit higher, or if I shift it the other way, read a little bit lower, just because the scale is, a couple of millimeters behind the needle. So what you'll see is for high precision gauges, there will actually be a mirror right behind the scale. And that way you can basically line up the needle with its reflection as a way to ensure you're looking straight at the gauge. So the other thing you want to consider about taking measurements is whenever we're talking about different measurements, what we really mean is we want independent measurements where one measurement does not depend on the results of any other measurement. And particularly if I'm going to average out several measurements, I want them to be independent of each other. So a quick example of this is if you look at this dummy graph, you can think of, okay, I want to measure the wavelength of these waves here, right? So I've got these peaks at A, B, C, D, and E. So I can make one measurement of the wavelength by measuring from peak A to peak B, right? But now if I try and make a second measurement of peak B to C, well, both of those measurements depended on what B was, right? So A to B and B to C are not independent measurements. In fact, I could get the same thing. If I average A to B and C to D out, that's the same thing as taking the measurement of A to C and dividing by 2, right? It doesn't even matter what B is, because if I average those two values out, it's going to give me the same thing. However, if I take A to B and then I take C to D, those two measurements are completely independent of each other. Neither one depends on a common set of points. And this is something specifically you want to watch out for during the SCEDAR-SAT calibration, because you're going to be doing something like this to find the fundamental frequency. If I'm looking at where peaks are when at different frequencies, if I share the frequency on different harmonics, which is something you'll see when you get to the calibration, those aren't independent anymore. It's the same exact thing as this. And then another key point that you want to think about when you're taking your measurements is how much data do you need to collect? How many data points do you need? So in general, you want to apply or compare your data to some sort of model. And we usually do that by doing some sort of fit to it, right? It could be a line, it could be an exponential curve, but the idea is I'm going to compare my measurement to some predicted values based on some formula. So you want to make sure you have enough measurement, enough points to tell if your model is a good representation. And you're usually doing some sort of fitting to calculate some coefficients from that model. So you want to get enough points that you get good values for those fit. But one thing to be careful of is, depending on the number of coefficients I have in the equation, I can pick a low enough number of points where I can always make it exactly fit, right? So for example, if I'm just doing a linear fit and I have 2 points, well, I can always pick an equation for that line so it goes exactly through those 2 points, right? And what that basically means is those 2 points aren't particularly meaningful for me to be able to tell anything about how good the data fits that line. And this scales up. So basically, in general, if you have X number of coefficients, so the easiest way to see this is with a polynomial. So if I have like a second degree polynomial, a quadratic equation, I'll have 3 coefficients there, right? I'll have A, B, C. A squared x plus bc, or plus bx plus c, right? For any 3 points, I can always pick an A, B, and C so that it'll go exactly through those 3 points. So in general, you want to get more, a larger number of data points compared to the number of constants you're using in your fit. Also, this is the reason why in general, if I go into Excel, I can go ahead and I can do like a 13th degree polynomial fit on a set of data. But that doesn't really tell me anything because, I at that high of a polynomial, you can basically make it fit any data. So, you want to try and keep whatever you're fitting with something that you have an idea of why the data should look like that, but you want to have an idea of what that is before you start taking data, so that you can make sure you can get enough points to see if it matches. The other thing that you want to do is consider how spread out your points need to be. So if I zoom into any sort of arbitrary math function, any sort of curve, if I zoom in on one little section of it, it'll look like a line. So I want to get a spread of different data points wide enough that I can be sure that my model and my data will match over that range, right? In particular for the SkeeterSat, that means, yeah, I want to try and get down to close to zero, and I want to, heat the water up 50, 50 degrees C, maybe 70 degrees. It sort of depends on how safely you can heat the water and how reasonable you can get the data, right? So conversely, there becomes a point where it's not really helping you to take any additional data points, right? In general, you tend to think more data is better, but at a certain point, you're not really learning anything more from the extra data, right? Especially this ties into our early discussion about systematics. Once my averages, get within that systematic error, or there's no point in trying to take measurements at every quarter of a degree if my thermometer only reads out in single degree increments, right? Like a good way to think about this is I cannot continually measure the length of something and get it with a ruler and get an accuracy down to nanometers just by repeating the measurement with a simple inch ruler over and over again, right? And then the other consideration of, looking forward to fitting is in general, it's better to be able to interpolate, that is, look between your data points as opposed to extrapolate. A lot of times you have to extrapolate, look beyond the range of your measured values, but that can be a little bit tricky, right? So the behavior can change over different ranges. So you may have a sensor that's linear over, one set of values, but once you get outside of that value, it starts to change its behavior. Maybe it's a quadratic or exponential. So you want to try and pick measurement values, again, to give you a good spread so that you can look at it over that particular range that you actually measured. So all of this sort of ties together and the reason we're covering this now is so that you have this stuff in your mind when you're taking your measurements for your SkeeterSat calibration, right? So we want to take steps to minimize our schematics, or our minimize our systematics. So that's the sort of things where I want to, try and group my thermometer and my temperature sensor together. I want to make sure that I record my beeps as close to me actually looking at the thermometer that I'm using to measure the temperature with, right? One thing that you can do is make a number of repeated measurements on an initial measurement, just so you get a size of that random error. And then using that, you can use that to guide, okay, this is how many measurements I need to take to get my random error down to some particular level. You want to estimate, you want to go into the experiment with an idea of what the behavior you're expecting to see, so that you can make sure you take sufficient data to either confirm the behavior that you expected, or to see that it that it was different than what you expected. And usually what you're going to do for that is you'll look at your data sheets for your sensor. You'll look at the theory of operation. Depending on what the theory or the actual physical process that you're trying to study, there will be some sort of model or theoretical basis that you want to look at before you actually start taking measurements. And then also, to aid in your analysis later, you want to record, what tool did I use to make this measurement? What scale, what setting was it on? So that I can then go back and actually make an assessment of those systematic errors. So that is it for the error lecture. Are there any questions about that? Either from anyone in the room at LSU or anyone remote?
They're good here, Aaron.
Okay.
Aaron, I have a question. This is McNeese.
Yes.
So in the sample report, the graphs include the statistical confidence level, or the bar graphs, if you
Right.
will. So my question is, for every temperature, how many beeps do we measure?
Well, it's the sort of thing where there's not really a right answer. So what I would say is the way I would argue it is, hey, I repeated this measurement X amount of times, like on one measurement, this was the random error I saw. And then my systematic error, say, I'm looking at it of a temperature down to 1 degree, because that's the thermometer I was using, right? So my systematics are, that big. So if I basically need, this is how many measurements I needed to take to get to where my systematic is my, dominating effect, right? It's more of, we're looking for students to just think about it and put forth an argument, rather than, oh, we want you to take 5 points or 5 measurements at, every 10 degrees or something like that, right?